How are you today?
I'm good. How are you?
Good. All right. I was looking through some of my digitized material that I have in my computer that students have sent me throughout the years for taking Trig. I thought what we might do today is go through some of those and just have you take a shot at some of these.
Yeah, sounds good.
Okay. About number 1. I want you to find the value of the trig function and write it in lowest terms.
Okay. 12 over 9.
Okay. Simplify that.
So 1 and 3/12. I mean 3/9. So 1 and 1/3.
Yeah. When you're trying to simplify something like that, what you're doing is you're looking for the greatest common factor between those two numbers. What number will divide evenly into both, and the biggest one? And in this case, it's 3. So I'm going to divide the top by 3 and the bottom by 3, and actually, I prefer that answer.
Okay.
To a proper fraction, only because the nature of trig is all about ratios. So the moment we turn that into 1 and 1/3, we've lost that beautiful ratio of 4/3.
Okay.
Okay. And how about number 3?
So 9 over 3. So just 3.
Okay. And up here, number 2.
So, opposite 8 over 6.
Simplify it.
4 over 3.
Okay. Number 4.
15 over 20. So 3/4.
Okay. Number 5. Find the cosine if the sine is equal to 12/13. Work me through the process. What would I do?
Cosine, isn't the sine just the reciprocal of cosine?
No, it isn't. Sine is reciprocal of cosecant.
Oh, okay. So
remember it like this. You have your 3 primary functions that are on your calculator keys.
Right.
Each one of those has a reciprocal. So there's no way sine could be the reciprocal of cosine.
Right.
And start at the bottom, you know that is the reciprocal of cotangent. So now there's 2 others. There's secant and there's cosecant. Which one goes with which?
Cosecant goes with sine, and then cosine goes with secant.
Right, because everyone has a co in it.
Right.
Even though these are not cofunctions. Cofunctions are something totally different. In fact, as long as we're talking about it, I don't know that I have talked about it. Have I? Well, it's really easy. To get the cofunction, you put the word co in front of it. In other words, the cofunction for sine is cosine. The cofunction for tan is cotan. And the cofunction for secant is cosecant. Now, what is special about these? It's that they share this property. All of them. And vice versa. In other words, we've been talking about the sine of 30 degrees. You know that that's 1/2. Well, we also know the cosine of 90 minus 30 is 60, and the cosine of 60 is also 1/2. So if you take the complement, in other words, I could say that the sine of 41 degrees is the same as the cosine of 49 degrees.
Okay.
That's the property of cofunctions. And similar to reciprocals, these have exactly one co in them, but it's always in a specific spot. It's always in front of the name.
Okay.
Okay, so that's cofunctions in a nutshell. This case here is the case where they are giving you one trig function and they're asking you about others. If you have one trig function, you can give all 6 trig functions. What's the first step here?
Make a right triangle.
Right triangle. And more importantly, label theta. Okay, now what can I do? If the sine of theta is 12/13, which sides can I label?
You put the opposite in the hypotenuse, so the opposite would be 12, and then the hypotenuse would be 13.
Now finish labeling the triangle, or finish dimensioning it.
So, let's see.
This is actually one of your special triangles.
So 5.
Yeah, there's a 3, 4, 5, which is the lowest right triangle. And the next lowest is 5, 12, 13. And it would behoove you to memorize both of these, only because they get presented to you so often. If you have to go through the Pythagorean theorem to figure out this 5, then let's just review that. They've given us the hypotenuse and one side, so this is always the square root of 13 squared minus 12 squared, which is the square root of 25, which is 5.
Okay.
But you don't want to have to do that any more than you absolutely must.
Right.
And when they're giving you one of these special triangles, you don't have to do it. So.
Okay.
Okay, so the cosine of theta?
13 over, wait, no, sorry. 5 over 13.
Okay. As you can tell, trig is primarily a lot of just memorization. Tell me how to do this one.
So right triangle. And then, you have to label theta. And, opposite would be square root of 7. And then adjacent would be 3. So
this one you're going to have to do the math. So this is the square root of what?
9 plus 7.
Or 4.
Oh, okay.
Okay. In other words, that became the square root of 16.
Right, yeah.
Which is 4. But it's always, even when it comes out to be an integer, the way you should memorize it is that unknown side starts out square root up.
Right.
And that way you will always know immediately what to go into. And you don't have to go all the way back to a squared plus b squared equals c squared.
Right.
So what's the cosine of theta?
3 over 4.
Okay. You notice it didn't matter which angle I labeled theta, as long as you label one of them.
Right.
You can't really go anywhere if you don't start out by labeling theta. How about number
Okay, so,
This time I'll label that as theta. And incidentally, I probably don't have to say this, but theta is never the right angle.
okay,
Theta is always one of the two acute angles.
right.
Okay.
So, the hypotenuse is 25, and then the opposite is 7.
25 squared, this is actually another perfect one, I think.
Oh.
I believe it is, but it's 25 squared is 625, I think.
625?
Minus 49 is 576, which I believe is the square of 24. Do you have your calculator?
Yeah, hold on. Yep, 24.
Okay. I thought that's like the fourth or fifth lowest. You go 5, 12, 13, and then there's another one in between.
Mm-hmm.
Okay, and you know what the tangent is, 7 over 24. All right. Now, I think you're in good shape on those kind of problems. Let's go. Now, do these without your calculator.
Okay.
As long as it's a common angle, by common I mean a multiple of 30, 45, or 60,
Mm-hmm.
then you want to be able to do all those without your calculator. Doesn't mean you have to do them without it, but you'll be tested on it. So you
Okay.
want to memorize those. You don't really need to memorize what the tan of 45 is. You just have to be able to draw the two triangles.
Okay.
And I'm going to let you dimension these for me.
Alrighty.
It's this side,
That would be 1.
this side,
Root 3.
and the hypotenuse,
2.
and the other one.
And then 1, 1, and root 2.
Okay, good. And the tan of 45.
Okay. 1 over 1. So just 1.
Tan of 30.
30 is 1 over root 3, so root 3 over 3.
Okay. Cosine of 60.
Cosine of 60. 1 over 2.
And secant of 45.
Secant, let's see, 45. 1 over 1, so just 1 again.
No, secant's the reciprocal of what?
Cosine.
Okay.
Oh, 1 over root 2. Or, no, it would be switched, so root 2 over 1.
Okay, good. And then that doesn't need rationalizing.
Okay.
Now, I don't know if I mentioned this to you, but they may actually give you this triangle. Like this.
Mm-hmm, yeah.
Same triangle. It's 45, 45 triangle. And the only thing they've done is multiplied each side by square root of 2.
Mm-hmm.
And the reason they might give it this way, some schools prefer this way because when you do your sines and cosines, they're already rationalized. In other words, the sine of theta is root 2 over 2. You don't have to rationalize it. But obviously, if we were doing the secant, this one would give you 2 over root 2, which would have to be rationalized back to root 2.
Mm-hmm.
So this doesn't really make any more sense than this one. It works a little bit better with sines and cosines, but worse with reciprocal functions. So
Okay.
I remember this one only because I call these my unit triangles, much like the unit circle. The radius is always 1. Well, my unit triangles, the side opposite the smallest angle is always 1.
Okay.
But clearly you can remember, these are all relative. It wouldn't matter if I made that 10, made that 20, and put a 10 in front of that.
Mm-hmm.
Ratios are all the same. And it's ratios that trig is all about. So. All right, let's do some radians. Sine of pi over 4. What's pi over 4? There's going to be a period where you're going to have to do these translations.
Okay.
But, I mean, in the beginning, you're going to probably have to translate it to degrees in your head. But after a while, it's like a foreign language. You've really mastered a foreign language when you can think in the foreign language. You know what I'm saying?
Okay, yeah.
So, instantly, I recognize that as 45 degrees. And the reason is that pi over 4 equals 45 degrees. If it's always just pi in the numerator, then these two things always have to multiply to 180.
Okay.
Okay? And that's a good way to memorize. The ones you probably should memorize as quickly as possible are these three.
Okay.
Pi over 6 is 30 degrees, pi over 4 is 45 degrees, and pi over 3 is 60 degrees. And of course, pi over 2 is 90. Those four. And they're easy to memorize because in all cases, these two numbers multiply to 180. And then when you get things like 3 pi over 4, you can either use the conversion factor, 180 over pi, or you can do it like I was suggesting yesterday. If I wanted 3 pi over 4, then I'm just going to multiply that number by 3 to get 135.
Okay.
Okay, so I'm going to erase that. So what's the sine of pi over 4?
So that was 45, so 1 over root 2, so root 2 over 2.
Okay, cotangent of pi over 6.
So that was 30, so tangent, 1 over root 3, so root 3 over 3.
Okay, cotangent's the opposite of tangent, reciprocal of it. So tangent of 30 would have been 1 over root 3, but cotangent's actually root 3 over 1, so you don't need to rationalize it.
Okay.
Okay. Oops. Cosecant of pi over 6.
So that's 30. 2 over 1, so 2.
Good. And finally, cotangent of pi over 3.
Pi over 3. That was 60, so is 1 over, no, root 3 over 1.
It's 1 over root 3, rationalized to root 3 over 3.
Okay.
But remember, cotangent is the reciprocal of tangent. Tangent is opposite over adjacent. So tangent of 60 would be root 3. The cotangent must be 1 over root 3.
Okay.
Okay. All right. Let's see. I think I don't have anything else on this page, but I got some others. Yeah, this is slightly different. And stuff we have covered. You have your calculator in front of you?
I only have the one on my phone because I'm renting.
Does it have trig functions on there?
Let's see.
Well, there's actually...
Yeah, it has the 3 basic ones.
Okay. You're getting a calculator for class?
Right, yeah.
A TI-84?
Inspire.
Inspire, okay, good. We won't do these calculator problems then.
Okay.
Just because, I mean, that's not a bad thing to practice on. You'd want to be able to make sure you knew the secant, how to do the secant of 188 degrees. Because that's not a common angle. Come on, Ruger. Excuse me, sorry.
You're fine.
Dog just came barging into my office. Okay. All right, 19, we can do 19 through 22. You remember how to do these?
Kind of.
They've given us the domain. The domain is the first quadrant. In other words, these are only first quadrant problems.
Okay.
What they're basically asking for here is to solve for theta. Well, there's a couple of ways to think about this. There's the definition that cosine of theta, if that equals 1/2, then by definition, theta equals the inverse cosine of 1/2. But the other way to think about it, in other words, that's by definition, okay?
Mm-hmm.
So if we're solving for theta, you could put this in your calculator. But this is one of the common angles, so let's not solve this by calculator. In fact, all 4 of these questions are the common angles. Which angle on there, look at this picture and figure out which angle would give you a cosine of 1/2.
60.
That's the answer. $20.
All right. Cosine. 30.
21. And this is something you won't very often see. An irrational denominator. In other words, they did not bother to rationalize this. I suppose to help you out a little bit, or to help this student out. Because it's easier to figure out theta if it's not rationalized.
Right. 60. Okay.
And 22, hold on.
Okay. 30.
What would the tangent of 30 be?
1/, so 60.
Yeah, it must be the other acute angle.
So it's, yeah, okay.
Okay. In other words, if this one gives you a 1/√3, the reciprocal is going to give you a √3/1.
Mm-hmm.
All right. Now these, how are these different? notice problem 19 is identical to problem 23, including the domain. The only thing is they've defined this in degrees and they are defining this in radians.
Oh, okay.
Okay. So typically you want to give your answer in radians.
Okay.
If your domain has been defined in terms of radians, generally they want their answer back in radians.
Okay.
I mean, guessing a little bit, but that'd be a good practice for you anyway. Actually, I think these drills are excellent for you, and you're doing very well at them.
Okay.
You're going to start out on trig as a piece of cake. Unfortunately, we've only covered maybe a fourth of trig.
Right.
So that you got lots more to study besides what we've covered, but you should have a good head start on it. Well,
okay.
So theta is what in terms of radians?
So that's 60, so pi over 3.
Remember those two numbers have to multiply to 180.
Mm-hmm.
So 60 times some number has to be 180.
Right.
Tangent of theta equal 1.
So 45, so pi over 4.
Correct. Now notice that if they gave us a different domain, our answers might be different.
Mm-hmm.
If this domain said pi to 3 pi over 2, meaning the third quadrant,
mm-hmm.
then this answer is not 45, it's 225.
Mm-hmm.
So the domain they give you is very important. And if they give you a domain that goes from 0 to 2 pi, which is the most typical domain you're going to run into, well, let's do that. Let's do these same two problems, only let's make our domain 0 to 2 pi.
Okay.
So what would all of the answers be for cosine, or for theta, for 23? We've already figured out that 60 degrees, and you can give these to me in degrees if you want.
Okay,
So 60
so
degrees was one answer. And our domain is theta is going to go from 0 to 2 pi.
So that's the fourth quadrant?
Correct?
Okay. So
an angle in the fourth quadrant is equal to that 60-degree angle.
330?
300.
300,
The
okay.
formula, yeah, remember the formula is 360 minus theta.
Oh, okay.
Okay, so I'm solving for that theta. That has to be equal to 60 degrees.
Okay.
Well, if I take the theta to the other side, bring the 60 to the left, I get theta equals 300.
Okay.
But this is always the equation you want to use to figure out what that theta is going to be.
Okay.
Okay. And also know that if you're drawing it, remember the concept of reference angles. There's the 60-degree angle.
Right.
Well, whatever angle that is, this reference angle has to be 60 also. Remember that the reference angle that is made with the x-axis, no matter which quadrant you're in, is the same as that first quadrant angle.
Okay.
And that makes this line 300 clearly, since all the way around is 360. So if I'm 60 degrees short, got to be 300.
Okay.
Okay. What about tangent theta? Oops, I didn't mean to erase that. Tangent of theta equals 1. Where does that occur? I'm going to make this 360 degrees. Since I'm doing it a little bit harder, let's leave it in degrees instead of radians for the moment.
Okay.
It's harder to convert some of those others. Like 300 degrees is one right off the top of my head, that's 5 pi over 3. So I've gotten pretty good at making those conversions without going through that conversion factor.
Yeah, right.
And I do it really based on pi over 3 is 60. So I'm 1 pi over 3 short of 2 pi. That's 5 pi over 3. Okay, so that's kind of how I do that one in my head, but we'll do it in degrees. So tangent of theta equals 1. Where does that occur?
Okay, so 45, and it's in the fourth quadrant. So 315.
Tangent's positive in the third.
Okay.
Remember, all students take calculus. So sine is only positive in the second, tangent's only in the third, cosine's only in the fourth. They're all positive in the first.
Okay.
So a positive 1, we're looking at the third quadrant. We've already come up with the first quadrant answer. That was 45 degrees.
Okay.
Remember? Yeah, I think the easiest way to do this really is not to use those equations, but to envision that that has to be 45 degrees.
Yeah, right. But even though it goes to 360, you still have to make it positive?
What's half of it go to?
Half of it?
Yeah, in other words, if we know that the two angles we're talking about are that 45 degree angle in the first, and this angle that goes from here to here in the third.
Right.
Well, what is that angle? If this is 180 to go half a circle.
Oh, 210?
225.
225.
In other words, you're adding 45 to 180.
Okay.
Is what you're doing. Just like in the other one, I was subtracting 60 from 360 to come up with 300. But in this one, in the third quadrant, the simplest thing to do is to take your first quadrant angle and just add it to 180. And in fact, the formula is, in the second, it's 180 minus theta, but in the third, it's theta minus 180. So the way you solve for theta is to add the 180 to whatever's on the other side of that equation, which in this case would be 45.
Right.
All right. This is actually a much better exercise when you're doing all 4 quadrants. What about this one?
Um,
25.
So 60.
Okay.
And let's see. Tangent, so it would be in the third quadrant again.
Okay.
So 240.
Uh-huh.
Okay.
Yeah, you're just adding the 60 to this 180.
Right.
And down.
Okay. So 30.
Okay.
And you'd be in the second. So
it's whatever is supplementary to 30. Because again, we're looking at some angle where this is going to be a 30-degree angle.
Right.
So what's supplementary to 30?
Would it be 120?
150. Supplementary is they have to add to 180.
Oh, okay.
Okay. So 150 and 60. Excuse me. The first answer was 30, right? Yeah.
Yeah.
30 and 150 are correct.
Okay.
Okay. Now, this one, the calculator problem. Incidentally, 99% of anything that's not 40, 30, or 60 degrees or 90 or multiples of those is a calculator problem.
Okay.
We don't have any way to get the trig functions of 26 degrees. There are some other angles where we do have ways. There's half angle and double angle formulas, which you'll learn later. But I'm not sure that's easier. You'll have to. In other words, you can do things like 15 degrees, and you can do things like 22.5 degrees. Only because those are half angles of our common angles. But something like 26 degrees, you would have to put that into a calculator, which I can bring up and do. But first, give me the trig equation that would allow you to solve for both sides, both of the short sides of that. What would the first one be?
The sine of A, or 26.
Sine of 26 degrees is equal to
X over 11.
Yeah, CB in this case over 11. And so we can solve for CB. And what's the other equation that would allow us to solve for CA?
CA, the tangent. Wait, no.
We can actually use tangent at this point only because we now know a CB. But if we were doing it from the get-go, we don't know CB or CA, so we wouldn't want to use tangent.
Right. The cosine.
Here's cosine. Cosine of 26 degrees is going to be CA over 11. And those are just numbers. Once you put a number in there, you can solve for CB and CA.
Okay.
It's the equation. Solve each triangle. Now, when you're solving a triangle, the task is actually to put all three sides and all three angles on it.
Okay.
So the only angle we left off here was angle B. What's angle B?
Hold on. 64.
Okay. There's two really good skills in trig and geometry. And those skills are being able to subtract numbers from 180 or 90. In other words, finding the complementary number to 26 is a good skill to have.
Okay.
Finding the supplementary number to 26 is another good skill. That have 154. In other words, because that's what you end up having to do a lot.
Okay.
All right, let's look at 28. We're going to solve that whole triangle, and let me bring up my calculator here. Where was I? Okay. First of all, let's write our equations. Now, we could solve for number 28. We could solve for AB using the Pythagorean theorem. But that's probably harder.
Okay.
Because first of all, 9.5 squared is going to have decimals all on it. And then we're going to have to take the square root of that. We're going to have to use a calculator either way.
Okay.
It's easier to solve using trig. No, it isn't. Excuse me. Well, it depends. Now, let's solve this whole triangle using just trig. So, how can I figure out what angle B is? What equation? Always begin your trig equations with the trig function. Don't ever start with 3 divided by 9.5 equals something.
Okay.
Start it with the trig function. What trig function is going to allow you to calculate angle B?
Tangent?
tangent of angle B is equal to what?
3 over 9.5.
Okay. Which means angle B is equal to what? Inverse. Remember, when we find angles, we're going to use inverse trig functions.
Okay.
Looking for sides, we're going to use regular trig functions. But the first step here is to find an angle, because we don't know either that angle or that angle.
Okay.
But once we find that angle, now we can use the other trig functions to find the hypotenuse.
All right.
So the easiest step, I think, is angle B is equal to the inverse tangent of this number here. And the way I would do that on this calculator is secant inverse tan, and then 3 divided by 9.5 end paren. Whoops. Something didn't happen there, right? Oh, I do that every time. I cannot force myself to, I got to use my keyboard instead of this. In other words, I have to use this keyboard here, and I repeatedly use my own keyboard. I know. So this is 3 divided by 9.5. End paren, enter. Now, the one fault these calculators have is they don't tell you whether you're in radians or degree mode. In other words, I can't tell by looking at that answer. And the Inspire is the same way, unfortunately. And in fact, the Inspire is a little worse. The Inspire, on these calculators, it's real easy to hit mode and see that I'm in degree mode, third row down.
Okay.
Got either radian or degrees. Well, clearly I'm in degree mode. So that answer must be in degrees. Yeah, with the Inspire, it's trickier. There's an odd key combination you have to do.
Yeah, I think I kind of did it last year.
Yeah, to figure out whether you're in radians or degrees.
Yeah.
So anyway, so we now know angle B is, I'm going to round it off to 18 degrees. And now what? In other words, now we have that much of the triangle. Can we solve for any other angles easily?
Yeah. The tangent of the other angle?
Well, how about just real simply, what's the third angle in this triangle?
Oh, you just subtract.
Yeah.
Okay, so
subtracting from 90 again.
72.
Right. Like I said, you're going to have to do that a lot.
Yeah.
So now we've solved everything but the hypotenuse. So what trig function will let us, we got the choice of all 6 trig functions if we wanted.
Okay, to solve the other side?
Right, the hypotenuse, the only one we haven't solved yet.
Okay. So the sine of 18 is equal to 3 over x.
Which means that x is equal to 3 divided by the sine of 18.
Mm-hmm.
Okay. All right. Let's see what else I got here. We don't need word problems yet, but Incidentally, let's go back. No, I erased it already. Word problems in Trig always convert to triangles.
Mm-hmm.
Okay? In other words, a typical word problem in Trig is there is a flagpole that's 10 feet high, and if you point a surveying tool at it, your angle of inclination is 28 degrees. How far away from the flagpole are you? So that would be a classic word problem. And they wouldn't give you this picture. They would just give you all of those words, and you have to draw the picture and get enough information that allows you to finish solving the triangle.
Right.
And all you need is one angle. As long as you know that's a right angle, then you only need one of the acute angles and one side to solve the triangle.
Right.
Let's take a look at this real quick. We didn't cover these graphs. What kind of graph is that right there? Just looking at it, can you tell real quick? In fact, let me blow this up a little bit. It's kind of a sine. If I was starting there, it would be a sine. So I could make a couple of statements. It's a sine that has been phase shifted by 4 pi to the right.
Okay.
Right? Because this thing says 4 pi under that black line.
Okay.
But the other way to look at it is if you're looking at it from that point there, what is it without any phase shifts at all?
Cosine?
Negative sign.
Oh.
Notice that that is a reflection of the sine curve over the x-axis.
Right.
And the one thing to remember to distinguish cosine from sine, the most important thing, especially when you're trying to graph them, is sine always starts at 0 and goes up.
Right.
Cosine always starts at its peak, 1, and goes down.
Okay.
So if this whole curve were started here, it would be a cosine curve.
Okay.
So I could also say that this is a cosine curve phase shifted 2 pi to the left. In other words, I can put a lot of, let's just go through that. That might be helpful, actually. There's a lot of ways to state this curve. As I said, it is the sine curve of x minus 4 pi. It's also the negative sine of x. And it, thirdly, is the cosine of x plus 2 pi phase shifted to the left instead of the right. So if I'm going to pick one of those three, the convention is to always use the least phase shift. So I'm never using this one. I got my choice between minus sine of x or cosine of x plus 2 pi. Well, this is much better.
Yeah.
Okay. And just as here's a pretty cool problem, a Ferris wheel problem. It's going around in that direction. If you're trying to model a Ferris wheel, and you have people getting on right there, I'm going to use a non-phase shifted sine curve. Why? Because I'm getting on at the middle point, just like the sine curve starts at the middle, goes up, comes down to the middle, goes down, and goes up. It's exactly what's going to happen to these people getting on this Ferris wheel. They're going to get on in the middle, they're going to go up, and they're going to go down to the middle, then they're going to go down to the bottom, and then they're going to come back up. So sine curve models this situation perfectly. If I was getting on down here, which is probably the way most Ferris wheels are, platform is at the bottom, I'm not going to end up using that same model, because my model is I start at the bottom and go all the way to my peak. Well, what does that? A negative cosine curve. You see what I'm saying?
Yeah.
In other words, remember that these curves are going to be used to model hundreds of different things, from Ferris wheels that have a periodic performance, to breathing, to tides, to seasons, to all kinds of stuff. So this concept of knowing what it does in the beginning allows you to figure out, you know, if I give you the radius of this Ferris wheel and the speed that it's going around once, then you have everything you need to model it using a sinusoid function. And the key part is this principle. If I got on over here, well, that starts at the middle, goes down, comes back up. This is going to be a negative sign.
Okay.
Because it's the reflection of the sine. In other words, it starts at the middle, goes down, comes up to the peak, comes back down. That's negative sine. Now, if I were to start right here, my platform is not at one of those key points, then I got a phase shift in there.
Okay.
In other words, I'm not starting right here. I'm going to be probably using a sine curve that's phase shifted. So I've got to go up a little bit before I get to this point. So my curve might look like this. And notice this much is the phase shift.
Okay.
So these can get kind of complicated, especially when they involve phase shifts. But we're not going to get into that now. That's way too advanced for beginning you. What is this curve here?
That's
I wouldn't expect you to know, actually. Let's just go over. We've gone over sine, cosine, and tangent, correct?
Yeah.
Tangent had asymptotes. In fact, all the others have asymptotes. Tangent's always increasing like that. Notice tangent of 0 is 0. Tangent of 45 degrees is 1. Although that's not usually ever on that curve, that point. That point is not considered a key point on that curve. I never understood why it isn't automatically labeled as 1 there. Cotangent. Notice the tangent goes from minus pi over 2 to pi over 2.
Okay.
Well, the cotangent goes from 0 to pi before you hit its vertical asymptote. And there's actually a vertical asymptote right there also. You can't take the cotangent of 0. If the tangent, if this is true, well, then the cotangent would be the reciprocal of that. So the cotangent of 0 degrees would have to be something divided by 0. That's where you get vertical asymptotes. So wherever the reciprocal function is 0, you're going to have a vertical asymptote on these other functions. And cotangent is always decreasing. And then there would be, of course, another period of it over here. And that would occur at 2 pi. So every pi you have a vertical asymptote, and one cycle of it is right there, 1 pi cycle of tangent. Now notice that a period on the tangent is only pi. It's only 1 pi. Whereas the period of sine and cosine are 2 pi.
Right.
So that's an important distinction to make also. Now, let's just briefly talk about the other two, the secant and the cosecant. The way I almost always do these is by drawing the sine curve. And I know that when the sine is equal to 1, well, the cosecant must be equal to 1, right? Because the reciprocal of 1 is 1. So they both share that point. And the cosecant looks like this. One period of the cosecant sits on the tops and bottoms of the peaks of the sine curve. So now notice the sine is 0 there, so we're going to have a vertical asymptote in my cosecant. It's also 0 there, so we're going to have a vertical asymptote there.
Okay.
And another one there. And now I can erase the sine curve, and I'm left with my cosecant curve.
Okay.
Okay. And again, the cosecant curve has a period the same as sine. It's 2 pi. It's just, in other words, this is not one period. This is 1/2 of a period. This is the other half. Notice something else. What's the domain? Well, the domain of cosecant is all reals except multiples of pi.
Okay.
And that's exactly how you'd say it. It would be all real numbers except multiples of pi. And 0 is a multiple of pi. So that's not in the domain, pi is not in the domain, 2 pi is not in the domain. The range is what?
1 to infinity and then -1 and -infinity?
Well, yes, basically. I mean, if you were putting in an interval notation, it would be a little bit different than that. But yeah, basically, all reals except -1 to 1.
Okay.
Non-inclusive, because it can be equal to 1.
Okay.
Which means that if somebody said the cosecant of x is equal to 1/2, that's not possible.
Okay.
Any more than the sine of x could be equal to 1.1. That's not possible either. And there's a lot of trig where you end up solving the problem and you get down to this point and you know that it's an impossible triangle because the law of sines told you the sine of x was a number greater than 1. And so that tells you that that's not a possible case. And the last case I'll mention real quickly is the secant. And the secant sits on the tops and bottoms of the cosine curve. There's the cosine curve. So the secant is going to be that and that. Now I'll erase my cosine curve, and there you have the secant, and it also has vertical asymptotes wherever these things head off to infinity.
Right.
Actually, wherever the cosine is 0. Notice the cosine is 0 at pi over 2. So I'm going to have a vertical asymptote on the secant there.
Okay.
And secant also has a period of 2 pi, same as its reciprocals.
Okay.
Okay. You've had Trig 101. Well, maybe not. You might have had part 1 of Trig 101. But you've had a lot of Trig, and it seems to me like you've picked it up pretty good.
Okay.
So I will let you go because I do have an 11 o'clock.
Alrighty.
I will maybe talk to you again later.
Okay.
Okay, Emma. Bye-bye.
All right. Bye-bye.